This screencast is Law of Conservation of Matter, screencast number 2 or part 2. One thing I hope I can make clear and that you haven't misunderstood is that when you disassemble your carbon dioxide and water molecules and break them all apart, make sure you've kept them all together and that any extraneous other color atoms and unused bonds are not on your work area right here. So you're working only with the 6 CO2s and the 6 waters so that you can demonstrate that they're conserved when we get over to the second part of the reaction here. So after you have broken apart all of your atoms and bonds, they're going to be reassembled into 1 glucose molecule and 6 oxygen molecules. So I want you to start with the 6 oxygen molecules. And so that will be the red atoms, and there are 2 oxygen atoms for each oxygen molecule. So you'll have, as shown over here, your 12 oxygens, and then all you need to do is add bonds to them to assemble them with double bonds. Once you have completed that, then we'll move on to how to create the glucose molecule, which is a little more complex to put together. So these are the directions for assembling the glucose molecule. I'll go back and forth with this one. First, you link the carbon atoms together in a string, and it doesn't matter which sprocket you use to connect one carbon atom to another. It will all work out. So just put them 6 carbon atoms all in a line. Once you have done that, you will then add 1 oxygen atom and form a ring with a spoke, as shown in the next picture. So here we have your 6 carbon atoms. 1, 2, 3, 4, 5, 6. You had them initially laid out in a roughly straight line. Now you're going to insert an oxygen atom and connect it to one of the carbons so that you will have an oxygen and then carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, which is bound to the oxygen, and a 6th carbon sticking out as a spoke. So again, that's 1 oxygen atom to bring the ring together, and it's attached to carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, but not attached to carbon 6, which is going to stick out as a spoke. So you've done the first 2 steps here of assembling the glucose molecule. Next, you're going to assemble what's known as functional groups, which are groups that will attach to this main ring. For that, you'll need to set aside 7 hydrogen atoms just by themselves and 5 sets of OH, so 5 atoms of oxygen bound to an atom of hydrogen. So you'll just set them together and set them aside. I'll go forward to a picture in just a minute, but you're going to add an OH, this functional group here, to carbons 1, 2, 3, 4, and 6. So let's see what that means. Okay. So this is your OH, your oxygen and hydrogen. You're going to attach this oxygen that's stuck to your hydrogen. Use as many bond tubules as you need, and you will attach this unit to carbon 1. You will again attach another very similar unit to carbon 2, and then another hydrogen and oxygen to carbon 3, another hydrogen and oxygen to carbon 4. Carbon 5 you won't do anything with, and carbon 6, the one that sticks out as a spoke, will get a carbon-hydrogen combo. Okay, after you have completed step 4, you'll move on to step 5, which is attaching 1 hydrogen to carbon 1, 2, 3, 4, and 5. So you have your one hydrogen, which is simply the hydrogen or the little white molecular piece, and a bond will go to carbon 1, same to carbon 2, same to carbon 3, same to carbon 4. And you can't see it, it's not shown in this diagram, but if you can imagine this is three-dimensional, right behind this carbon atom, carbon 5, there's another sprocket, and sticking off of it is a hydrogen atom. Okay, once you've done step 5, you will be left with 2 hydrogen atoms, which you will bond to carbon 6. So you take your 2 remaining that are just a hydrogen atom and a bond, hydrogen atom and a bond, and attach those 2 to the 6th carbon, the one that sticks out as a sprocket. Now you have a completed glucose molecule. And all you need to do to make it very similar, same representation is here, is to twist the little pieces, the little sprockets and the bonds, so that they're shaped in this direction. So again, I want you to know that it's a three-dimensional structure. Unlike the real molecule, though, these bonds are oversized. They're not drawn to scale. So that this carbon, for example, and this oxygen are very, very close together. The length of the bond is simply to make it easier for you to work with. So after you've completed building your glucose and your 6 molecules of oxygen, I want you to consider whether mass was conserved during the process of photosynthesis. Did you have the same number of atoms on each side of the equation? Was energy conserved during photosynthesis? Did you use up all of the bonds, the chemical bonds that you had on the left side of the equation? Did you use them all up and no more to build the right side of the equation? And last, to further solidify this idea in your mind is to look at the process of respiration. And in respiration, what had been the products here become the reactants, and the reaction progresses in this direction, and then these are the products. And just to let you know, sometimes people write respiration in this direction. Other times when you see it represented, they will actually take the glucose and the oxygen molecules, write them on the left-hand side of the equation with an arrow, and move these products to the right-hand side. Same idea, just a different representation. And then again, answer the 2 questions. In the process of respiration, was matter conserved and was energy conserved?